Right, so in chapter 14, we're going to focus on Earth because we've talked about all the other planets, and so now we're going to discuss Earth. So the Earth is round. Hopefully this is not news to you. We're going to talk about some reasons why we know it's round. So during the 5th and 6th centuries BC, the ancient Greeks decided the Earth must be round for the following reasons. Philosophically, a sphere was perfect shape, and the Earth is perfect, therefore the Earth must be a sphere. The Earth was observed to cast a circular shadow on the moon during a lunar eclipse, still something we see now. The ships were observed to slowly disappear below the horizon as they sailed off to the distance. If the Earth was flat, you would see them until they fell off. The altitude of the North Star above the horizon appears to increase as a person travels northward, meaning the closer you get to the North Pole, the higher above the horizon the North Star appears to be until you're directly beneath the North Star. So they were correct. Also, we know that other planets are spherical, and there's no reason why we would live on a flat planet when the rest of them are spherical. So, as it turns out, the Earth is not a perfect sphere, though. It is officially called an unsymmetrical oblate spheroid, meaning it's kind of a sphere, but not quite. Oblate is because it's slightly oblong. If this was a perfect sphere, an oblate spheroid is kind of bulged out on the sides and squashed down on the top and the bottom. It's kind of like those ab balls that somebody sat on. So it's flattened at the poles. There's an equatorial bulge. However, it's not even perfectly circular. There's a little bit of an uneven distribution of how oblong it is. The North Pole is slightly higher, South Pole slightly lower. Elevations and depressions with deviations less than about 85 meters. There's a lump in the Pacific Ocean and a depression in the Indian Ocean. So not perfect, but they were correct back in the 5th and 6th centuries BC that we are living on a practically spherical planet. So the sun and the planets appear to us here on Earth in the sky in an area that's called the ecliptic plane. So each night, the sun will rise and will travel along this plane and along with the planets. So the planets will also travel along this as well. And what we see is that as we go through winter to the summer, the sun may go from here in January, then in March, and then, maybe this is June, and then in July it's going to reach its highest point, and then it's going to start working its way back down, which is why we have longer summer days than winter. The Earth has 3 distinct motions. There are some other motions which are inconspicuous, meaning we don't really discern that they're happening, but the 3 that we know that are happening and are independent of the motion of the sun and the galaxy, meaning they're just earthly motions. We revolve around the sun every year. We rotate daily on our axes, and we also wobble on our axes. And we're going to talk about the wobble. So to start with the orbit, we are going to make one complete movement around the Earth, around the sun every year. Roughly, it's 365.25 days. Because every 4th year we have what's called a leap year, and that's a year where we have 366 days instead of 365. So that takes into account the quarter of a day. The orbit defines that plane of the ecliptic we talked about. The ecliptic is the apparent path of the sun and the planets moving through the heavens as we see here on Earth. Now, when we orbit around the sun, we're not making a perfect circular path, but what's called an elliptical orbit, which is a little bit more shaped like this, meaning at times we're going to be further away from the sun, and then other times we're going to be much closer. So we are actually 2.5 million kilometers closer during the month of January. We are 2.5 million kilometers further away in July, which for us is our hottest months, but that's because in June and July we're receiving direct sunlight as opposed to in the wintertime where we are not receiving direct sunlight. The Earth receives approximately 6% more solar energy in the month of January. So the Earth's rotation axis is not up and down like a spin top. We're tilted just 23.5 degrees as shown. So if this is the North Pole and the South Pole, we are tilted just a little bit to the side, and we're rotating around that tilt. What this does is give us seasons determined by the orientation of that axis. We have the winter solstice, the summer solstice, the spring equinox, and the autumn equinox. The equinox is where we have equal day and night, so we have an equal number of day hours as night hours. And the summer solstice is going to be the longest day, and the winter solstice is going to be the shortest day. And they're determined based on how we are positioned around the sun. The celestial equator is different from the ecliptic plane because the celestial equator is going to be the direction of the sun's motion. There we go. It's going to be where our celestial bodies rotate around. If this is the ecliptic plane, right here in blue, then the celestial equator is going to be the one that's tilted 23.5 degrees along with Earth. And then you'll see here, this is the North Star, which is right directly above our North Pole. So does the Earth really spin? We have evidence from other observations. One is going to be that we know that other celestial bodies rotate. So Jupiter, the sun, we can travel or observe a sunspot moving over a period of time. And so that tells us that we are probably rotating. We have what's called a Foucault pendulum. Sometimes they have these in museums and they're pretty neat. But the pendulum will oscillate in a fixed direction and changes its orientation as Earth rotates. So each day, the pendulum is going to start off and it's going to swing back and forth. And then it's going to change its position a little bit. And the pendulum just swings back and forth. And it takes all day to do this. So I don't have all day to do this. But what you see is that it's going to eventually make its way all the way back around. And then this would be the next day. And so this tells us that the pendulum, which should just swing back and forth, unless it's on something that's rotating, which then distributes the sand to make this really pretty pattern, which confirms that we are moving. The next one is the Coriolis effect. And there's going to be a YouTube video for you to see the Coriolis effect because it's something that doesn't make sense until you see it illustrated for you. It's a very quick video. What this is it's a deflection of paths because Earth is rotating beneath the moving objects. And so if you're in the northern hemisphere, things are going to deflect down. In the southern hemisphere, they're going to deflect out. Now, the video you're going to watch is essentially speeding up the rotation because they're on a merry-go-round. So it's kind of like Earth, but the Earth is not spinning around as fast as a merry-go-round. But it's a deflection that occurs, which tells us that the Earth is spinning based on what we know about things like being on a merry-go-round. Now, the precession is the one that's called the wobble. So the wobble is probably an unofficial term. Precession is the official term. So this is the reaction of the Earth to the gravitational pull on its equatorial bulge by the moon and the sun. So remember when we talked about the universal law of gravitation? Well, it becomes really important because of the relationship with the moon. They are two large bodies of mass within a certain distance of each other. They're applying a force, an equal and opposite, and the moon is going to cause a lot of unique things on Earth, and one of them is this wobble. So it takes us 26,000 years approximately to make one complete wobble. Okay, so it's very slow. It's not a fast motion at all. But what happens is we're changing the direction of the rotation axes on our celestial sphere. So remember that line in pink that we saw. Now what this means is all of the stars that are around us, while they're fixed, we are moving around. We hopefully figured that out whenever we talked about that in chapter 12. What this means is over time, Polaris, which is currently our North Star, will not always be our North Star. In about 14,000 AD, the next North Star is going to be called Vega. So what this means is the position of the equinoxes in the zodiac will also change. We're going to take a break and then we'll pick up on the rest of this chapter in the next.